Good morning. Today we are going to do the proof of Taylor's theorem, which states that there are three statements for this theorem. First one is, let fz be analytic in a domain D whose boundary is C. If z0 is a point in D, then fz may be expressed as fz equal to f of z0 plus f dash z0 over 1 factorial z minus z0, where f dash z0 is the first derivative at z0. That is, the first derivative of a function at the point z0. Then f double dash, that is the second derivative of a function at the point z0, over 2 factorial z minus z0 whole square up to so on, where if I sum up all these infinite terms, then I will be getting the nth term, that is fn z0, z minus z0 the power n over n factorial, where fn z0 is the nth derivative. Second statement is, which can be stated as, every function analytic in a domain is the point-wise limit of some power series. Third one, every function analytic in a domain may be expressed by a power series. So this series is nothing but your power series, which is expressed as. So let's start with the proof. Let fz be analytic in a domain D whose boundary is C. This black color boundary is drawn as your C. Let z0 be a point in D. Suppose I am having a point z0 in this domain D. And let delta be the distance from z0 to the nearest point on C. Suppose this point to be taken as the nearest point on C, and the distance from z0 is taken to be delta. So this distance is delta. Then construct circle C1, which is centered at z0, having the radius rho. And now one more circle is constructed, that is C1, this outer circle, such that now the points contained on C1 will be as T. Okay, so I take any point on the circle. Suppose I have taken this point T. So T minus z0 mod is rho, that is the radius of this, or a distance from the point z0 to the point T is rho. So take this as your rho. Obviously this rho is less than this delta, because this delta is your distance from z0 to the boundary C, and this rho is the distance from z0 to the circle C1, and C1 circle is contained in this boundary C. So obviously this delta is less than delta, this rho is less than delta. So rho is less than delta. Fine. Let z be any point inside C1. Now again I have to take a point inside this C1. Suppose z can be anywhere, here, 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 here. That is the inner circle. I am taking z over here. And let the distance from z to z0 will be your radius r. Take this distance to be as r. Alright. So then what can you say about this r? This r is further less than this rho. Alright. Okay. Now this C1 is a circle, and I'm having a point Z inside this C1. Obviously Z0 is also there, but Z0, because this C1 circle is centered at Z0 and Z is any other point. So I will apply the Cauchy's integral formula over this C1. So let's start. Then by Cauchy integral formula, as z be any point inside C1, so by Cauchy's integral formula, f of z is equal to 1 over 2 pi iota integral over C1 f of t over t minus z dt. Okay, see, on C1 the points are of the form t. Alright, that's why the integration will be for t only. Alright, okay, and also we are having z minus z naught, this is as r, and r is less than rho. Okay, taking this denominator and this 1 over t minus z, let's solve this first. 1 over t minus z. First of all, I have to simplify this denominator, which is equal to, I'm adding and subtracting z naught, okay, which is equal to, taking t minus z naught outside or common, is this clear? Okay, now next thing is, which is equal to, now opening this binomially, get this denominator in the numerator and open it as binomially. So this will be 1 plus z minus z naught over t minus z naught plus z minus z naught over t minus z naught whole square plus n minus 1th term n minus 1th term plus, because the sum because the number of terms are infinite, so I am taking the rest of the terms as summation, which is, now the next term will be the nth term, so I start with n and up to infinity, t minus z naught the power k. Alright, next, now what to do? I will, now this is your sum of infinite series, or this is a sum of infinite terms. Now this sum is GP, so whenever you are having in geometric progression the number of terms are infinite, then what is the sum for GP? The sum will be, wait, first I write the terms 1 over t minus z naught, 1 plus z minus z naught t minus z naught plus z minus z naught square t minus z naught, okay, whole square it is, z minus z naught over t minus z naught whole n minus 1 plus. Now what is the sum for GP series? Infinite sum is first term over 1 minus the common ratio. Now what is the first term for this summation? This is z minus z naught over t minus z naught the power n. This is first term over 1 minus, what is the common ratio? Same, z minus z naught over t minus z naught. Alright. Now taking the LCM and t minus z naught, cancelling this, and also I am taking this t minus z naught inside. Okay, so let's take t minus z naught inside, and for the last term taking the LCM, and something will cancel it. So I'm writing the main step, which is 1 minus t minus z naught plus z minus z naught t minus z naught whole square plus z minus z naught. Okay, this will be z minus z naught over t minus z naught whole square, then z minus z naught square over t minus z naught cube. So on z minus z naught power n minus 1, t minus z naught the power n, and the last term will become z minus z naught over t minus z naught whole power n into 1 over t minus z. Take this as your 1. Next, now what you need is, we have simplify this 1 over t minus z. Okay, now what we have to do, we have to multiply this ft on both the sides. Okay, so multiply f of t to the equation 1. So this become f of t over t minus z equal to f of t over t minus z naught plus z minus z naught ft over t minus z naught square. So on z minus z naught the power n minus 1, f of t over t minus z naught the power n, plus the last term z minus z naught the over t minus z naught whole power n, f of t over t minus z. Now we have to integrate both the sides. So integrating both the sides, and integral is over c1 ft over t minus z dt. This is your n minus 1/12 term. Why I am taking all these outside? Because integration is with respect to dt t. So I have, so z minus z naught can be taken outside. this can't go outside because t is contained in this fraction. So this can't be taken outside because t is included. So take this as your 2. And now what we have to do now, we have to apply the Cauchy integral formula to this equation 2. So apply Cauchy integral formula to equation 2. So what will we get? This will be left hand side 2 pi iota f of z. Then 2 pi iota f of z naught. Then z minus z naught 2 pi iota f of z naught first derivative over 1 factorial. Then so on. This will be z minus z naught the power n minus 1 2 pi iota f of z naught and derivative n minus 1th derivative. Okay, and over n minus 1 factorial. And the last one, in the last term Cauchy integral formula cannot be applied. So what we have to do, just because we need to cancel 2 pi iota all over, so here what we have to do is just multiply numerator and denominator by 2 pi iota so that I can cancel 2 pi iota whole. Now all these 2 pi iota get cancelled and we will be getting f of z is equal to f of z naught plus z minus z naught over 1 factorial f dash z naught plus z minus z naught whole square over 2 factorial with double derivative, so on, z minus z naught the power n minus 1 over n minus 1 factorial f nth n minus 1 z naught plus, what about this last term? Now 2 pi iota is cancelled all over, so we will be left with 1 over 2 pi iota integral over c1 z minus z naught over t minus z naught the power n f of t over t minus z dt. Take this whole term to be as Rn. Just denote this as Rn and take this equation as 3. So I'm taking this equation as 3. Okay. Now, can you see this? If this Rn tends to 0, then we will be having the required result. This only we need to prove. Okay, so we have to take this Rn and we have to show that the mod for Rn is 0 or Rn tends to 0 as limit n tends to infinity. Alright, so just we have to show now that Rn tends to 0 as n tends to infinity and we will be getting our required result. Now the result follows if we can show that limit n tends to infinity Rn equal to 0. Alright, for this, see, our function is continuous on C1. As C1 is taken to be as a closed interval because it is a circle, so f is bounded on C1. Okay, whenever your function is continuous on a closed interval, that function is bounded. So we can attain a bound that is m for fz. So let's write that. Since f is continuous on C1, therefore f is bounded on C1. Thus we are having mod of fz. Let's take this less than equal to, we attain a bound for function on C1 for some positive real number m. Alright, now taking mod for Rn, let's have this Rn. Okay, in the next page, let's start. Mod of Rn is equal to, what is Rn? 1 over 2 pi iota integral over C1 z minus z0 over t minus z0 the power n f of t minus z dt. This is your Rn. This mod is further less than equal to, what is mod for iota? Mod of iota is 1. So 1 over 2 pi iota mod, that is 1 over 2 pi integral over C1. This is mod of z minus z0 the power n, mod of t minus z0 the power n, mod of f of t, mod of t minus z, mod of dt. What is mod of ft? Just now we have written this is less than equal to m. And what is mod of z minus z0? We know that this distance is r. And t minus z0, this distance is rho. So just write that. This mod of ft is less than equal to m. This is r and this is rho. Take this like this is m. Now here I am adding and subtracting z0. You know why? Yes, you know that. Again, this is less than equal to 1 over 2 pi integral C1 r over rho the power n, and this is mod of t minus z0 minus mod of z0 minus z. Why? Because 1 over mod of a plus b is less than equal to 1 over mod a minus mod b. Okay, so this is equal to m over 2 pi r by rho the power n and t minus z. This is t minus z0 is rho and z minus z0 is r. And this integration mod of dt. Integral for mod of dt is nothing but your circumference of the circle C1. and C1 circle has a radius rho. So what will be the circumference? 2 pi rho. So this is m over 2 pi r over rho the power n 1 over rho minus r. This is 2 pi rho. Just cancel this 2 pi with 2 pi and we'll get m rho over rho minus r by rho the power n. Now what is r by rho? Is this less than 1? Yes. See, we know that r is less than rho. So r by rho is less than 1. So if we take a limit n tends to infinity and this ratio is less than 1, then this whole will become that tends to 0. So since these two things happen, so limit n tends to infinity r by rho the power n, this is 0. Alright, so letting n tends to infinity on the equation, take this as your fourth equation. Limit n tends to infinity mod of Rn is less than equal to, because less than equal to sign starts from here, from the very starting point less than equal to sign comes. So I'm writing here this is less than equal to 0 because this thing is 0 when n approaches infinity, which is equal to, okay, for your convenience I'm writing this again. So limit n tends to infinity mod of Rn is equal to 0, which implies limit n tends to infinity Rn is equal to 0. So letting now n tends to infinity on the third equation, where we take this last term as your Rn. Now letting here n tends to infinity in this third equation, we will get the required result. Z minus z naught over 1 factorial f dash z naught plus so on z minus z naught the power n minus 1 over n minus 1 factorial f n minus 1 at z naught up to infinity, which can be written as summation n going from 0 to infinity fn z naught over n factorial into z minus z naught the power n, which is the required result. See, if you put n equal to 0 over here, 0 factorial is 1 and f0 z naught means no derivative, and you will be getting f of z naught only, and z minus z naught the power 0 is 1. So first term will become f of z naught only. When put n equal to 1, you will get your second term up to so on. So here the proof ends up. And also you should know that Power series represents an analytic function inside its circle of convergence. But Taylor's theorem is essentially the converse. Here, the function fz is analytic at a point, this z0, if and only if fz can be expressed as power series. Alright, and if your z0 point is 0, that is origin 0, then this Taylor formula will be changed into that series. That formula will be known as Maclaurin's formula. So here we have to write the remark for Maclaurin's formula. What is the Taylor's formula? See, if we put z0 equal to 0 in Taylor's formula, we get f of z is equal to summation n going from 0 to infinity, nth derivative at z0, and z0 is 0, okay, over n factorial, and z minus z0, since z0 is 0, so I have to write only z, the power n. Alright, so this is nothing but this is your Maclaurin's formula. So in the next video, we will be doing some exercises in which Taylor series, Taylor's formula is used. And so thank you for watching this video. And if you need my new course, that is real analysis, you can check the description box. And thank you for watching this video. Goodbye.